Calc BC 4-8 lesson. It's just going to be kind of extension of the last lesson, but do a few more complicated examples of finding the area in polar curves, and you'll have an opportunity to try some like that on today's assignment, which is how I'll do. So first thing I would say is sketching these is going to be super helpful. This is a rose curve with 8 petals, radius of 2. It's even. So you usually want to figure out where the tips of the petals are. So that's going to be plus or minus 2 equals 2 sine 4 theta. And that's going to become plus or minus 1 equals sine 4 theta. So 4 theta equals sine equals 1 at pi over 2 plus pi k. And theta equals pi over 8 plus pi over 4k. And so it's going to be pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8, 9 pi over 8, and so on. I think I can get away with drawing pretty good drawing without writing all those down. But there will be 8 distinct petals. So I don't really know if it's necessary to draw the sketches on all these now. The next problem after this, for sure, sketches are going to be very, very important. So I'm going to sketch a circle. Roughly fits that our rose curve will fit inside of. So pi over 8. So we need to do pi over 4, and pi over 8 is going to be halfway between those. So there's pi over 8. And then here's 3 pi over 8. And here's 5 pi over 8. And here's 7 pi over 8. So the circle is going to start here at pi over 8. And that's going to be a positive petal. So that's going to be the first petal. The next one's going to be back here at 3 pi over 8. It's going to be negative. And then 5 pi over 8 is going to be the third petal. And then 7 pi over 8 is going to be negative. So that's going to be the fourth petal. And then so pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8. And then 9 pi over 8 is going to be here. That's going to be the fifth petal. And 11 pi over 8 is going to be backwards. That's going to be the sixth petal. And I don't even know what we're on now. 9 pi over 8, 11 pi over 8, 13 pi over 8 is going to be positive. It's going to be the seventh petal. And the last one's going to be over here. That's going to be the eighth petal. So the graph's going to go like this. Goes like that. Goes like that nicely into the fourth petal, nicely into the fifth petal, nicely into the sixth petal, nicely into the seventh petal, nicely into the eighth petal. There we go. Getting good at drawing those rose curves. Okay, anyways, formula for the area inside a polar shape is 1/2 r squared d theta. We derived that from the area of a sector and said, okay, there's infinitely many. Now the area of this whole curve would take 0 to 2 pi. If it was an odd number petal rose curve, it'd be 0 to pi because the second sets are right on top of the first sets. And then you plug the radius in that you've been given and you square it. You could do that, or you could say, hey, there's 8 petals. Let's find the area of one petal. And so the area of one petal, like say for instance, first petal would be 0, this angle to that angle should be pi over 4. And then you have 2 sine 4 theta squared inside. So you could do that. You know, I don't really know if that's better. I think I'd rather plug in 2 pi than pi over 4. But anyways, just actually you could square the 4, the 2, that would give you 16 in front. And so anyways, I mean, you could do that. I'm not gonna finish the calculation now. We're definitely getting enough practice on that on homework and stuff like that. But The setups are really what I want to focus on today. Now, this one's interesting because this is going to be the area involving two shapes. So without a sketch, I don't really know how you pull this off. The first one is a circle, and the second one is a cardioid. So I think we really need a decent sketch of these to kind of figure out what we're even trying to find, because we're only trying to find pieces of them. So the first, the circle, theta 0, we only need to go to pi. So we plug 0 into that, you get 3, 0, 3. And then the next one, the cardioid, we're going to go 0, pi over 2, pi, 3 pi over 2, 2 pi. So you plug that in there, you're going to get 2, 1, 0, 1, 2. So I'm going to graph these together. So I'm going to make this graph a little bigger because this graph is going to be really helpful to us. So we're going all the way to 3. And let's see. So I think we're going to really need a good graph of this. So, okay, so 0, 3 is right here. Pi over 2, 0 is here. So that's a circle. The circle has a radius of 1.5. So we're going to go like this. So that's a circle. And the cardioid is 2 here, 1, 0, 1. So this is the cardioid. Now, it says we're looking for, I don't know, trying to make that a little better. Okay, so it says we're looking for the area. Let's see, the area that is between these. So I guess that you can interpret that different ways. The area between these. So you have the circle. I'm going to go, okay, it says inside the circle, outside the cardioid. So inside the circle, but outside the cardioid. So we're looking for this area right here. Now, what we need to do, we have to, like when find the area between multiple curves, last year, we definitely need the intersection points. So these intersection points, the angles that create those are going to be very important to us. That's going to be where we're going to start and end our integration. So need the intersection points. And so the way we find the intersection points is that's the place where both curves have the same radius. And we set one r equal to the other r, and then we're going to solve it. So this would be 2 cosine theta equals 1, cosine theta equals 1/2, alpha equals pi over 3, quadrant 1, quadrant 4. So theta equals pi over 3 and 5 pi over 3. Now, if you look at the drawing, this looks like about pi over 3, and this looks like about 5 pi over 3. So that's one benefit of the drawing, is that you even know where you're looking for these answers. But, okay, so now, when you find the area, here's our strategy. If you want to find the area, let's use symmetry to help us. Let's find this area right here. Now, when you find polar areas, you're finding it by slicing. So let's find this area from 0 to pi over 3 inside the circle, and then subtract the corresponding area in the cardioid to that same point. And so when you do that, you're going to get, so here's the circle, here's the cardioid. What's that's going to give you is going to give you this area right here. Okay. And then we'll double it. Okay. So we're finding the bigger area and then subtracting the smaller area to get this difference in here. And so when you go to set this up, it's going to be, we're going to double it, first of all, because we're only doing half right now. So it's going to be 1/2. And the first one is going to be 0 to pi over 3. And that's the circle. So that one's going to be 3 cosine theta squared. And then we're going to subtract 1/2, 0 to pi over 3 of the cardioid, okay? And so because it starts here at 0 and it's going like this, right? It's going like this. That's how you accumulate the area. And so we just stop it right there. We start it right here and we stop right there. So that one's going to be the other one. That's going to be 1 plus cosine theta squared d theta. So that's the setup right there. Now, I'm not going to finish it, but that's the setup. This one's kind of getting annoying here. So that's the setup there. But you kind of, I don't know, without the picture, I don't know how you would figure out, well, which one do I subtract from the other one? Where do I start? Where do I end? How do I use symmetry? I mean, I feel like the picture was very helpful in this problem. Okay. So I'm going to do some more on the back.